Saxon Algebra 2, Lesson 39. We've got one algebra topic and one geometry topic. Life is good. Let's do the algebra one first. Difference of two squares. We've talked about this in the past. What we're going to do is come at it from a different direction. We know that there are things called conjugates. A conjugate is, in its purest form, two terms, let's say 2x plus y, and when we create the conjugate to this expression, we keep the first term the same, and then we flip the sign of the second term. So this is a pair of conjugates. Another one would be 3x plus 4. We change this by making it, no, I'm sorry, that stays the same. My bad, 3x minus 4, okay? So the first sign stays the same. Let's do one. Where there's a minus sign out in front, okay? It's only the middle term that changes. Now, when we multiply conjugates together, they do a cool thing. Let's look at the first one. 2x plus y times 2x plus minus y. Sorry. My brain just doesn't want to live in the conjugate world. Let's see what happens. 4x squared plus 2xy minus 2xy minus y squared. These will cancel. We get 4x squared minus y squared. If you look at this pattern, it will always be the same. When we're multiplying conjugates, we will always get the square of the first term, the square of the second term, and a minus sign. Okay? So this is the first term squared, right? Because it was 2x, 4x squared. This is the I'll move this over a little bit. This is the second term squared. Let me write that like that. And there will always be a minus in between them. So this is super helpful because if we see a pattern like this, where we see a perfect square minus a perfect square, difference of two squares, we can automatically break it down into those two terms. We can automatically factor it that way. Let me show you in the problem. You probably remember this from last year. It's super easy. I'm just showing you a little bit more of the theory behind it. So let's look at the problems because you'll go, oh, okay. I guess this is really easy. Solve 4x squared minus 9 equals 0 by factoring. Okay, so we were doing this in the last lesson, right? We were solving by factoring, but this time we don't have a proper looking trinomial because where's the x term, right? It throws you off. What your brain needs to do is go hold the bus. This is a perfect square, and this is a perfect square. And we recognize that we have a pattern that looks like this. We have a value that's being squared, another value that's being squared, and a minus sign in between. And we can always break that down into the product of conjugates, all right? What we have to do is we have to break these values down and say, okay, if this is a squared, then what would a be? Well, the square root of 4 is 2. The square root of x squared is x. How about this b? The square root of 9 is 3. So now we have our values, and we can easily set this up, and we can say it will be 2x plus 3 quantity, 2x minus 3 equals 0. Now we can use our zero factor theorem to say, okay, if these two multiply together and they equal 0, then either 2x plus 3 equals 0 or 2x minus 3 equals 0. And then we subtract the 3. 2x equals minus 3 and divide by the 2. So x equals minus 3 halves, and then guess what this will be? We add the 3. 2x equals positive 3, divide by 2, x equals 3 halves. So those are the values for x that will make this come true. Do you feel smart? You should. One comment about this, you can write the conjugates in either order. You can memorize this formula by remembering a plus b times a minus b, or you can remember it like this. Or you can just use it different ways and different times, which is what I do. I just mix it up, whatever I'm in the mood for. You know, having moods for the difference of two squares as one does. Okay, so that's how we can use difference of two squares to solve some problems, and it gets us out of a sticky mess real fast. Example 39.2. Solve 81m squared minus 25 equals 0. Okay, the hardest part of these problems is just recognizing, oh, perfect square alert, perfect square alert. Yes, I have a minus sign. It won't work with a plus sign. It has to be a minus sign. So I'm going to find my square roots of each of those. This would be 9m. And the b is just going to be plain old 5. So now I can write 9m plus 5 quantity, 9m minus 5 quantity equals 0. And you'll quickly see that you can shortcut your way through this algebra really quickly. I'll show you what you do. We know that it's going to be m equals, this is going to change signs, and then it's going to be divided by that. Okay? So that's one answer. And then the other one, this will change signs. It will be positive 5, and then we'll divide by 9. So once you get the hang of how the algebra works, you can quickly step into the shortcut version, save some wear and tear on your wrist. All right, so that's how we do difference of two squares equations. There's your formula. Have some fun. Those are easy. Okay, we talked about parallelograms last time, and today we're going to talk about a special parallelogram. I want to draw you a little picture. I'm going to draw it for you next year. But I've had fun talking about this with Jayla and Laura and Vivian this year. These are all the parallelograms, okay? They live in a little house here. There are lots of different kinds of parallelograms. Some of them are rectangles. Some of them are what we call a rhombus. Those are the kids we want to talk about today. Rhombuses. And where the rhombus team and the rectangle team intersects, those are the squares. Okay? So last time we were talking about just the random parallelograms that live out here, right? Because we weren't talking about anything special. We were just talking about your garden variety parallelogram. And we learned they have 4 special properties. The sides opposite each other have equal lengths. The angles opposite each other, let me just draw a picture. This is your garden variety parallelogram. The sides have equal length that are opposite each other. The angles that are opposite are the same. The angles that are next door neighbors, so this angle plus, just a second, let me write that over again. The angle with 1 hashie plus the angle with 2 hashies equals 180. And the the diagonals bisect each other. This list, last time you wrote it in your notes and you wrote it in your cover, but I want to tell you that it is on page 177 if you'd like to revisit it, okay? These 3 rules, I'll show you. Dun, 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 dun. Okay, so John's gonna do a proof in here to prove to us that the diagonals bisect each other. We're just gonna let John have some quality time by himself there. We're not gonna worry about proofs in Algebra 2. Next year in Advanced Mathematics, we're gonna join the proof club, and then we're gonna go back and talk about all these things. But this year, it's too theoretical and you don't need it. Okay, so now what we wanna do is we wanna talk more specifically about these specific types of parallelograms, the rhomboids, if you will. And here's what's cool about the rhomboids. That's a made-up word. Don't let me trick you into believing that I'm speaking truth. All right, D, E, F, G is a rhomboid. All right, let me put these guys in a box. Okay, D, E, F, G is a rhomboid. Rhombus, I'm sorry, I have to stop saying a made-up word. A rhombus is a parallelogram. So all of these things are true. So all the parallelogram properties are true. Plus, we have 3 more. 1, all 4 sides have equal length. And in that respect, a rhombus is kind of like a squished square, right? So we can say this. These guys are all the same length. Okay, that's cool. 2, what else can we say? The diagonals bisect the angles. Okay, so what that means is when I draw this, there's the diagonal, it's chopping this angle perfectly in half. Diagonals bisect the angles. And P.S., that's true for all this pair of angles as well as these 2 and these 2. I'm not drawing them all in because it'll make a big cluttery mess, but it's true of all 4 corners, right? The diagonal bisects the angles. And then the last additional property of rhombuses is the diagonals of the rhombus are perpendicular bisectors of each other. What the heck does that mean? It's so simple. That means they form a right angle. So I'm going to shortcut that long sentence down to say diagonals form right angles. Okay, so where they meet in the middle is beautiful and perfect and square. All right, that's what perpendicular bisectors means. Okay, so we have one more problem, and we're going to use all 7 of these facts, right? The 4 original ones that we talked about that are listed on page 177, plus these new special properties to analyze some rhombuses. Oh my gosh, say that 3 times fast. You know, when your family asks you at dinner table tonight, so what'd you do today? You say, oh, I just analyzed some rhombuses using, you know, the special properties. NBD, you're just raising a genius. Okay, DEFG is a rhombus. There's a picture. It's got a bunch of letters in it. Okay, I'm gonna just start drawing because it's too confusing. Remember, a rhombus is like a square parallelogram. So I'm gonna try and make the sides look pretty even. Not bad. Okay, D, E, F, G are the letters. bisectors are drawn in, and as I'm drawing them, I think about the fact that these not only chop each other in half, but we've got that right angle right in the middle. I'm just gonna put that in because I think that's cool. Now we've got a bunch of letters floating around in here. A, X. And as I do this, I think, oh gosh, they're making angles out of each side. And then I go, oh right. In a rhombus, those are equal, aren't they? That's good to know. K, B, this one's C, what the heck? And then, as if all of this isn't crazy enough, we've got a circle out here with two little arrows on it, and it says 280 degrees. Okay, and the instructions say DEFG is a rhombus, thank you, we knew that. The measure of the reflex angle, remember the reflex angle is like the outside, it's the other part. So this is the reflex angle. You know that game that you play with your reflexes where you hold your hands? I'll be the under and you put your hands over me and I try to go over and slap really fast. I always think of that when I think of reflex angles. Find, the measure of that is 280. Yeah, we've got that. Find A, X, B, K, and C. All right. Well, John put these in a non-alphabetical order. He said to find A, X, B, K, and C. That seems really random, but the fact that he gave them to us in a random way makes me curious. So I'm going to try tackling them in that order. Let's look at A and see what that is. Those aren't ones, those are commas. Okay, angle A is here. All right, this I like. Sorry, I had to yawn. Not that I'm bored, because I'm having a really good time, you guys. Another way to start these problems is to follow the numbers. This is the only number that we've been given. Everything else is just letters. So I like the idea that we can use this number right away. What I know is this much is 280. So how much would this be? Well, it would be 360, the whole circle, minus the 280, which is on the outside, which tells us that that much that I've colored in, that has to be 80 degrees, right? And we know that X and A are splitting that. So that tells me that A has to be equal to 40 degrees and X must also be 40 degrees. Huh, I like it. So far, so good. All right, what about B is what John says to do next, but I disagree with him. Here's what I want to do. Let's look at this. A, we know, is 40 degrees. If we knew this corner, then we could do K because we know these three have to add up to 180, right? But look, all four of these make a 90-degree angle, right? So that means, I'm just going to draw this angle separate, this triangle separately. This is A, this is 40 degrees, right? And this is K, we don't know what that is. This one we know has to be 90 degrees because it's in the perpendicular middle. So that means that angle K over here has to be 180 minus 90 plus 40. Make sense? That adds to 130, so that means K equals 50 degrees. Ooh, I like it, right? Now, that takes care of K. K equals 50. What about B? Is there anything we can say about B? Well, B is sharing this angle with K. So these guys, we know that this diagonal bisects this bigger angle, and that B and K are the same size. So if K is 50, then B must also be 50. Oh, this is so fun, right? The math is super easy. It's just a question of trying to remember all of these crazy characteristics or properties of the rhombuses, the rhomboids, and applying them. And then our last one is C, and C is up here in the corner, and we've already talked about this. We know that C must be equal to 90 degrees because it's tucked in there up by that perpendicular intersection in the middle of town. All right, this should be it, right? 40-40, 50-50, 90. Yay, we got them all right. Okay, I hope those feel semi-fun to you. They're like detective problems. And as long as you can keep all of those properties clear in your head, there's the list of the first four for parallelograms. Parallelograms have all of those, or rhombuses have all of those same four properties plus 3 more. You're good to go. All right. Yay, that was lesson, wait a minute. That was lesson 39. I just here got crazy and called it lesson 38. Okay, I wasn't crazy all the way through. All right. I will see you for lesson 40 next time around. And good news, it's a single topic. Yay.